Just as a joke. Okay. Yeah. Good morning. Still some chairs are vacant. Okay, fine. My objective is very simple. Consider the deterministic optimal control as Nandakumaran was talking in previous, and then for those equations try to derive the dynamic programming principle, and from there you reach the Hamilton-Jacobi equation, first order equation, because we are dealing with the deterministic problem. For stochastic, anyway, I think Professor Ghosh will talk. So first few minutes I want to spend in describing the notations. Okay, I am right to left. So Rn is my state space, and I have the time. Okay, so horizon finite from 0 to capital T. So we have the equation. Okay, so because Nandakumaran was already introduced the system, very difficult. So T naught is my initial time. So where this is U, so we have a map. I always denote by U dot, because U fixed will not use U dot, but as such is a control input function U dot U, which is some other Euclidean space. So for simplicity, I assume that we take controls from compact state. It is not required, but for simplicity it is better. Then, so let us take the control inputs. Again, for simplicity, I take all U dot measurable, because it is compact. U is compact. It is very easy, no problem. So this is my admissible control space. Sorry. Okay. So now, if you fix my initial data, okay, initial state and initial time, and fix an input, control input so then we can ask for existence of a unique solution. So existence of a unique solution for this initial value problem. So I want to give set of sufficient conditions which are not the best possible assumptions, but for simplicity I stick to a stronger condition. Okay, so I assume that F is bounded, continuous, and uniformly Lifschitz in the state variable. Okay. We can reduce, simplify this, weaken this assumption, but for our purposes I think this is better. So this is true for every xy in Rn, and for every u in U, and for every t, and so on. So under this assumption, so This assumption is always in force. You always assume that. So under this assumption, we have for every control input u dot, every initial condition, we have a solution, unique solution. So that I use the notation, which maybe Nandakumaran was using a different notation. For the solution of that initial value problem, I use the notation, so which indicates everything. Okay. So initial condition is there, and input is there. Okay. So this notation is similar to what Kalman used in his 1960s work. Similar, not exactly, but similar. So we have the preliminary notations, existence uniqueness under the assumptions. So we have the control dynamic system is ready. Now we have the objective function. Okay. So J we have the time interval T0 to T. On that time interval, I use the control input u dot, start from x0 at time T0. Then what is the cost associated? Where phi is the notation I have given, phi is the associated solution. Again, for L and for G, we have some simplifying assumptions. So I assume that L usually we have similar assumptions as F. Okay. L bounded, L continuous, similar assumptions as F. Okay. For every xy, for every t, for every u, and so on. Okay. Then G simplicity, I assume that the G bounded, uniformly continuous. So G is from Rn to R. Okay. L is from Rn cross the time interval cross U to R. Okay. So for each control input, we have the output P and the associated cost J. Okay. So now, what is the minimum cost? Okay. So if you fix x0 and t0, you vary the control input, and this is the V x0 t0. This V is the value function. Value function. So clearly, for a finite horizon problem, it is a function of initial profile. Okay. Now we can state the formally, can state the optimal control problem. Okay. What is that? So for each initial profile, find the optimal control. That means find U star satisfying so U star is optimal control for the initial profile x naught t naught. So this is the basic problem. So how to find U star is the fundamental problem, and Professor Nandakumaran talked about one approach, maybe without proof, the Pontryagin maximum principle. You consider the system, we have already the system x dot equal to f, together with you consider the adjoint system psi dot or p dot equal to some adjoint system is there, you consider x plus together with the adjoint state, then you have so called Pontryagin maximum principle, necessary conditions, set of necessary condition for U star to be optimal. I am not going to that. What we are going is a sufficient conditions. So I want to derive some sufficient conditions for U star to be optimal. So to that end, you will look at the value function little more closely. So first, so those whoever has learned ODE formally would know what it is. It is not difficult. Ground wall lemma or inequality. If you don't like lemma, inequality. So it is very simple. If you know that alpha t equal to c plus d integral t naught to t alpha s ds, then I know that differentiate, I know that alpha dot t is d alpha t, then I know the solution, right? So I know alpha t equal to some constant exponential dt minus t naught. So if I know that this is this, and that will imply this. So ground walls lemma is inequality is nothing but, instead of equality I can put this, okay, that implies this, that is ground walls inequality. So if you state suppose we have alpha satisfying integral t naught to t alpha is ds, say almost everywhere t in t naught t1, then so I am not proving that, it's very easy, just reminding that. So that will give, because ground walls inequality will give us a continuity of the solutions of differential equation ODEs with respect to initial condition. Why? Because suppose you take phi1t which is phi which is t starting from x naught t naught and some u. Similarly you take phi2t which is solution starting from t naught, say some other y naught by the same control, only initial condition, state initial condition is different. So we know that P1 minus P2 P modulus is less than or equal to, okay, you use the Lifschitz continuity of the function f, you will get k, so you use the assumption a1. Okay, you have to put s inside. Okay, inside the integral you put s. Okay. So Grunwald's inequality immediately gives us use Grunwald you get to t less than or equal to so this if x naught equal to y naught, then we have a solution equal and so on. You get uniqueness, continuity with respect to the initial condition and so on, everything. Okay. Similarly, so this one we are changing the initial state x naught y naught t naught fixed. Similarly, you change say only t naught. You can do both together, but this for simplicity I am telling. X naught you fix and S naught you change. Okay. So similarly, you can go ahead and show that this is equal to the upper bound for f. Yeah, this is an exercise you can do, no problem. If you have done it earlier, similar things you just forget about that. You can show that. Just Grunwald's inequality and f is bounded. So this is a sort of this and this together says that if you vary the initial condition x naught y naught to y naught s naught, still our solution is nearby. So in other words, we have continuity with respect to the initial conditions x naught and y naught. This is very standard, and because of that we have the continuity of the value function also. Implies that j x naught t naught u minus j y naught s naught u. Okay. So u is same. What we change is initial condition. From the above two inequalities we get this is also less than or equal to some constant into basically for every t in a finite interval 0 to t. So and this constant is independent of the input u. Okay. So that you do calculation, it will be very clear. Okay. So you can take infimum and get the same bound for the value function, because the value function is nothing but the infimum over j. Oh, one point I missed. So if you look at back my assumption on A2, assumption A2, please go look back. Assumption A2 on L and G. L is bounded, L is uniformly Lifschitz. I think I assumed G is only uniformly continuous. So if I assume G Lifschitz continuous, I will get Lifschitz continuous here. But if we assume G uniform continuous, I will get only uniform continuity here. So let me correct here. Okay. So this is okay. Where this is the so-called modulus of continuity. Basically, this is an increasing function, and when you omega at 0 plus is 0. So when this goes to 0, this goes to 0, this goes to 0. So if we assume everything is Lifschitz continuous in the data, you will get Lifschitz continuity of the value function. Otherwise, maybe you may be able to show Helder continuity or some cases. Okay. So, but in general, I use the general terminology that it is uniformly continuous. You can show. Okay. So value function is uniformly continuous. So let me state that. Assume A1 and A2. the conditions about F, L and G. So under those assumptions, the value function V is bounded, uniformly continuous. So this is bounded because L is bounded, G is bounded, so V is bounded, uniformly continuous because of ground walls inequality. Okay. So this much we have done. So continuous, bounded. But unfortunately, it is not smooth. We cannot expect also. For a very simple reason that I will give an example, but what is the reason? You take very smooth functions, say e power x, e power minus x, for example, infinitely smooth. You take the minimum of those functions, what do you get is this only. Minimum of two continuous functions is continuous, but minimum of two C infinity functions in general is just continuous. You cannot get more than that. So this is not differentiable here. So as a reason, you cannot expect more than continuity for the minimum function. Okay. So we can give examples also. Just give one example. So t is 1, my time interval 0, 1, one dimensional problem. So fxtu is u. So it's actually a calculus variation problem because x dot equal to u. Then what else I want? So L is 0, there is no running cost. G, you can take a lot of functions, but let me take simplicity, tan inverse x square. So that is increasing, so 0 infinity, increasing, infinitely differentiable and so on. So all the data is infinitely smooth. But still you can see value function is just continuous. So that is exercise. So there is a difficulty also, because it is nice that it is difficult, otherwise we cannot talk about it, no. So what is the solution Pt for this example? Okay. X naught T naught U dot. For this example, so what is the equation? Phi dot T equal to Ut, right? Phi at T naught is X naught. The solution is very simple. So X naught plus integral T naught to T US ds. So T naught less than or equal to T less than or equal to 1. So what is J? So L is 0, so there is no integral term in the cost, only g of xt is there, g of x1, or g of p of 1, that is tan inverse p1 square. So I took x square just to make it smooth. You can do mod x also, but then it will not smooth, no. Now you can explicitly find V value function here, because it's a very simple example. Okay. So the idea is very simple. You will get the expression of phi. P is here. U, I did not mention. Nobody asked me also. U equal to minus 1 1. Okay. So I take functions u dot from interval t naught to 1 to minus 1 1. Okay. So the control functions are taking values from minus 1 to 1. So if you look at here, whatever control function you take, you can only take from minus 1 to 1. So I can adjust my control function so that this whole integral term can take values from minus of 1 minus T naught to plus 1 minus T naught. You cannot go beyond that. Whatever control function you choose, a minus of 1 minus T naught, or you can go up to plus 1 minus T naught. Okay. So because of that, what do we get? We can, because of that fact, in this case, it is 0 if mod x naught is less than or equal to 1 minus T naught, because in that case I can choose my u naught and I can cancel it with this. Okay. Otherwise, it will be tan inverse P1 square. So mod x naught minus 1 minus T naught square or something like that. So basically it is not smooth, it is not differentiable at all points. Okay. Not differentiable at. So despite the fact that the f, which is ftx u equal to u c infinity, g is tan inverse x square c infinity, l equal to 0 c infinity, everything is infinity, but still the value function is just continuous. It's not differentiable at all points. Sorry? Sorry. Yeah, because of mod x not coming, there is a problem. So those some points we have a problem. Yes. Oh. Okay, so that is finished. Okay. So this motivates. So I go back to our basic aim. So what was aim? Is that somehow find methods to derive or compute U star optimal control. Okay. For that we have to use V, or we use some differential equation satisfied by V. That is the usual way. You derive differential equations for V. Now, if you derive differential equations for V, you have to the solution has to be understood in a weak sense, because it is not differentiable. So that much it is clear. Right? So we'll go forward. So in what way we have to understand solution in the weak sense? Okay. So weak sense we have to always put in a quote. So yesterday Professor Adimurthy talked about weak solution in one sense, because the equation was linear. So we could do integration by parts and convert the equation to a bilinear form and use function analysis results like Milgram lemma, and we got existence, uniqueness, all that. So that is one way. But here it may not work. So I will explain why. Okay. So before that, my next task is to derive the differential equation for V. So for that we need some properties of V. Now we know only the continuity of V. So the next property of V, which is very crucial, is the so-called dynamic programming principle. So I want to come to that. So to that end, I define. Okay, so you start with the T naught and X naught also. T naught you take from 0 to T, and you consider interval 0 to T minus T naught. Take a delta in that. Okay, so delta lies between 0 and T minus T naught. In other words, T naught plus delta lies between delta and T, whatever you want to consider. And for such a delta, you define J delta. So it is similar to J. We know what is J, which is objective function. Integral T naught to T, L blah 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 dt plus G phi T. That is the original objective function. Here for this deltas, I define a kind of auxiliary auxiliary cost function, which is nothing but integral T naught to T naught plus delta. Okay. So on the interval T naught to T naught plus delta, I don't do any optimization. You do any arbitrary u. So okay, so you go with this u. I'm not optimizing. Okay. So let me put u hat, okay, just for convenience. So L of P of S u hat of s ds plus. Now from T naught delta onwards, I minimize, I choose the best possible value. So that is nothing but V so on T naught to T naught plus delta, where u hat is any control in T naught plus delta. So on T naught to T naught plus delta, I am not doing any optimization. So immediately, once you do that, immediately we have an intuition. So we don't need to calculate anything, we have an intuition. Oh, yes. Here T naught to T naught plus delta, correct, thanks. So from J we have V, similarly from J delta I can define V delta, so there is no problem. As Nance told yesterday, we are all greedy, so we don't stop anywhere. So V delta over all possible control inputs on the interval T naught to T naught plus delta, you define J delta, okay, and you minimize over that. Now we have an intuition. We have V delta. So which one is bigger? It's not difficult. Suppose you are asked for younger people to choose a partner today. Why? Suppose your objective is that you want to minimize the cost you are going to pay for that from today onwards. That is one way. So you get your V. Now another question is that you choose a delta, which may be 1 day, 2 day, 1 year or 2 year. Okay. So the next delta time, okay, next 2 years you choose any one, don't worry about the price. But after 2 years you choose the minimum. So which is bigger? So V or V delta is bigger. So if you think about my example, you know the answer. Right? So first 2 years you don't choose optimally anything. After 2 years only you are going to minimize. So most likely V is much less than V delta, right? Yes. So that is the intuition. So intuition says that okay. So if your initial choice is good, then V may be V delta, less likely, but otherwise it is strictly less. Okay. But we can show that. Okay, I am not based. I mean, completely dependent on my intuition. Sometimes it can be wrong. Okay. So I am going to prove that V less than or equal to V delta we can show. That is my next lemma. So for that, what you do? So you choose a T naught, T naught plus delta. In this, you choose any u hat. Okay, u hat. Then x naught, T naught you choose, u hat you choose. So it solve the differential equation. Okay. So this can be solved on the interval T naught to T naught plus delta, because the input is u hat is from T naught to T naught plus delta. You choose any u hat, x naught T naught you fix, solve the differential equation up to T naught plus delta. So you consider, where are you now? After delta time you are at phi T naught plus delta. Okay. Now as mathematicians never forget epsilon. So you okay. take any fixed but arbitrary epsilon positive, then choose we call u bar, which is from T naught delta to T, such that, so after T naught plus delta, you have to choose it optimally. If an optimal control exists, we don't have any problem, we can choose epsilon equal to 0, but then we have to go more details, right. So we now have to assume that optimal control exists, we don't want to do that. So that's why epsilon is chosen, and instead of optimal you choose an epsilon optimal. Okay, so choose such that V or J T naught plus delta, because we are at phi T naught plus delta at the time T naught plus delta, and you choose this u bar, it should be epsilon optimal. We choose such that, so that is less than or equal to V that is always possible. For any epsilon I can do that. So now we have the two control functions u hat dot and u bar dot, one on T naught plus delta, another on T naught plus delta T. So you consider the concatenation of both. That means combine them, define u star, u hat T, u bar T on T naught less than or equal to T less than or equal to T naught plus delta and T naught plus delta less than T less than or equal to T. Combine them. So u star dot is in the input from T naught T. Just concatenation of both u hat and u bar. Now it's very easy. J x naught T naught u star dot what you have to show? We have to show V less than or equal to V delta. Yeah, so, V less than or equal to V delta. Okay, that's okay, fine. So this is what you have to do. So this is integral T naught to T naught plus delta L phi of S u hat S ds plus J phi at the point so plus integral T naught plus delta to T L S hello yes okay, let me continue on that board. Okay. So V less than or equal to V delta. So J x naught T naught u star dot, which is equal to integral T naught to T L phi S u star S ds plus G of Pt. So split from T naught to T naught plus delta, and then onwards what we get? Integral T naught to T naught plus delta L plus J phi naught phi T naught plus delta T naught plus delta u bar. So this is less than or equal to integral T naught to T naught plus delta L plus V P T naught plus delta T naught plus delta plus epsilon. So this is J delta x naught T naught U hat dot plus epsilon. So okay, yeah, that is what we are done. So I am thinking. So J is less than or equal to V delta, I mean plus epsilon. So corresponding to the concatenated version, J is less than or equal to V J delta plus epsilon. J delta, yeah, that is correct. So now say this U hat is arbitrary. So before that, so I'll continue. So till now everything is okay. This implies that V x naught T naught is less than or equal to J delta because V is the infimum. So V less than or equal to J. Now epsilon arbitrary, U hat arbitrary. Okay. So you can take infimum both with respect to epsilon and U hat. So you get V less than or equal to J delta. Basic idea is very simple. So we have started with J, the original one cost function. Then we have the auxiliary cost function J delta for each intermediary deltas and corresponding V delta, and V delta is bigger. Once you know that, then we have the following. Next lemma, you consider delta going to J delta by fixing all other things, okay, fixing everything except delta, everything is fixed. Okay. So U hat dot is fixed, x naught is fixed, T naught is fixed, only delta is changed. So you choose your partner for the first day and for the first 2 days, first 3 days, that is varying. So this is so once you know V less than or equal to V delta, I think I will leave it as an exercise. It's not very difficult. Okay, so I have given in my notes. So it is there. It is not intuitively. It is okay, right? So if you fix, then delta as delta varies, this J delta keeps on increasing. Okay, that I leave it as an exercise. And just a remark is that immediately, what is J0? Delta equal to 0. Delta equal to 0. What do you get? J, right? Delta equal to 0, it is nothing but J, because T naught to T will come and the remaining things will come. So it is J. Then when delta is the final T minus T naught, what do we get? What will be the can you tell something about that? So what is the interval? T naught to T naught plus T minus T naught, that is so what you can say about so J naught is J told so what is this? So T naught to T naught plus T, so it is T naught to capital T plus V or so is it correct or not? What is when T equal to 0, delta equal to 0, what happens, sir? Delta equal to 0, it is T naught to T naught plus V. Yeah? So T, when delta equal to 0, what is that? You tell me, then I will go forward. Look at the definition of J delta.
So it is V of
G. Now you go back to the definition of V. What is V at capital T? Okay, so see that, okay. So it is V, okay. So at T equal to 0, it is V only, but here it is J. So you see, it is nothing great, you just the definition, nothing else. Only thing you have to keep in mind that by definition Vtx is a Gx. Okay, once you know that, then everything is there. Okay. Now what is V0? V0 is infimum of J0. J0 is V, so V0 is V. Now what is V T minus T naught? Infimum over J T minus T naught. That is infimum over J, so it is V. Okay, so you get V0 is V. Also you get V at the end time, because delta we take over the interval 0 to T minus T naught. So delta equal to 0, it is V. Here also it is V. And because you recall the fact that delta going to J delta is increasing, right? That we can show. Or intuition also I told. Intuition about choosing the partner. So because of that, this is also increasing. If you had delta going to J delta is increasing, so you can take infimum and show that this is also increasing. But at both points they are same. So it is a constant. So delta going to V delta is a constant function for each fixed x naught and t naught. So this the same thing I write in a fancy way, that is the dynamic programming principle. So dynamic programming principle for the value function, that is for x naught t naught in 0 t, not 0 t, Rn cross 0 t and the delta in 0 t minus t naught, V equal to V delta. Okay, V equal to V delta. I am just, instead of V delta, I am just writing the definition of V delta. In favor you had J delta, which I am rewriting, because in the standard statement you don't see V delta, J delta, okay. So this whatever in the square bracket is nothing but J delta. So in favor J delta, it is V delta. So right hand side as such it depends on delta, but actually it does not depend on delta. Appears to be depending on delta, right? So this is the dynamic programming principle. if we are considering the discrete time problem here. Okay. No, sorry, continuous time problem. Time varies continuously. If you consider the analogous discrete time problem, the same thing can be done there. So there, the delta variation is from step to step. You optimize from the first step, then from the second step. So this delta variation intuitively makes more sense. Okay. Optimizing from first step, then second step, and so on. Here, it's not a step, so it's similar, but okay. Now, from the dynamic programming principle, there are some things we have to learn. What are they? Which may be helpful in the sequel. So first thing is the following. Corollary, yes, none told we are never stopping. Corollary. So to explain, it is very clear. It's not very difficult. T naught plus delta, we have T. Suppose that on the interval T naught to T, corresponding to say some fixed x naught T naught, okay, that is always fixed in the background. Suppose we have an optimal u star dot on the full time interval T naught to T. Suppose you know that u star is optimal. Now you can consider the restriction of u star onto this interval and this interval. So let them be u hat dot and u bar, okay, like that. So consider the respective restrictions of u star onto the intervals T naught to T naught plus delta and T naught plus delta to T respectively. Okay. So what the dynamic programming principle, from there what we can conclude is the following. If u star is originally optimal for x naught T naught, then, so I am stating here. So if u star to T naught plus delta and T naught to T is such that it is optimal. So that means V x naught T naught is J x naught T naught u star dot. It is optimal. Then there are two things. One is that one is about u hat, another is about u bar. Okay. So about u hat, J x naught T naught u hat star dot. This is optimal for the delta problem. And another part is optimal for the next problem. That is about J phi T naught plus delta, and u bar, okay, u bar star dot, which is optimal for that V. Says that if u star is optimal for T naught to T, you break them up, each part is optimal in this sense. T naught to T naught plus delta, it is optimal for the delta problem, and from T naught delta to T, the other part is optimal for the original problem. I am not going to details of that, it is very easy, it is given in my notes. Practical? Yeah, actually for discrete time problem I can say is backward dynamic programming, that you start from the end and backward one step you solve, because suppose there are 10 steps, time steps, you want to find the optimal in all the 10 time steps. This says that you can start solving from backward. So you see from 9th step to 10th step, you find the best for that step. You fix that, then you come back to the previous state. Like that you can come back and solve the problem backward. So that is one implication. In interval, everything is fixed. In my case, T naught to T is fixed. So that a good question. But my problems always the interval, time interval is fixed. I am not allowing any change in the time interval. Simplest case. That we know. Time interval we know. In the discrete case, what you do is that you have the final time step. You find the optimal in the last one, fix that, and find the optimal here. Like that, you can come back. For discrete problem, I can explain that way. Basically, if you cut the optimal control, that control in both intervals, both parts are optimal in the sense I explained. So it is a kind of necessary condition for the control to be optimal. That way you can consider. And converse is also correct. So I can state that also. Converse is also correct. That means converse I can state. So if you had star dot is optimal, and if u bar star dot is optimal, then their concatenation u star is optimal. So their optimality, all that in the sense I explained here. J delta equal to V delta and J equal to V, like that. So both way it's correct. Okay. Yes.
U star is then defined as you had star in that particular interval and
Yes. A concatenation. First you had star, then followed by u bar. That's why I put hat and bar to denote the interval. Yeah, that's right. Okay. So once the dynamic programming problem is set now, I can derive the equation satisfied by V. That is the next thing. PDE for V. So it has two parts. First part is one inequality, another part is another inequality. So what I do is that I start. So as such, start with x naught t naught, and you consider t naught t naught plus delta, t naught plus delta t, like that. So if you look at the dynamic programming principle statement, it is V x naught t naught equal to V delta x naught t naught. In other words, it is infimum over all u dot. So infimum over all u dot, you can take any u dot admissible, any measurable. In particular, I use a constant control. So u dot is identically equal to some fixed u. Then what happens? So fix u dot is identically equal to some fixed u. Okay. Then you use DPP. So we have the corresponding solution phi t, which is phi t x naught t naught corresponding to the constant control. You can solve the problem on the whole interval. The corresponding trajectory is phi. Now by DPP, V is the infimum. So this has to be less than or equal to J, the cost corresponding to this constant control. So this is less than or equal to J x naught t naught u, okay, corresponding to the constant control. Okay, you just write that, and not J delta. So sorry. So maybe I'll rewrite. It is in over u dot, u hat dot integral t naught to t naught plus delta L plus V T plus delta. So this is the dynamic programming principle, nothing else. Same thing I am rewriting. This is for info over u. You take instead of u dot, you take the constant u. So I will get this is less than or equal to L integral T naught to T naught plus delta L, so phi T constant control U dt plus V the trajectory at T naught plus delta and T naught plus delta. So dynamic programming U dot equal to constant control U. So we have, instead of equality, we have inequality. So now you bring those sometimes into the left hand side, okay, rearrangement, algebra. So analysis people, when analysis people say that it's very easy, it's just algebra, then algebra people gets irritated. So, so it's just an algebra. So it is minus V divided by delta dt or ds, whatever. So this is just algebra. If any algebras are there, I want to irritate them. Then now you know what we have to do. Just pass to the limit as delta goes to 0, but assuming that V is continuously differentiable. Okay, otherwise we may not be able to do. Okay, so you assume that V is C1. Then let delta goes to 0. So now what happens to the first term? Yes. So you have to assume that so phi t is the trajectory. So phi dot t is f of phi t t u. Okay, phi dot t is f of phi t t u. So as t goes to delta goes to 0, t goes to t naught. This is it. So assume that V is smooth and take the limit. So this is the one-way inequality. Okay, this is true for every u. This is true for every u. Now to derive the equation, because our objective is to derive the equation, you forget about the rigor, so it will come back later, because we have to get hold of the equation first. For that you assume that there exists a u star dot optimal for the initial profile x naught t naught. Make that assumption and assume that t going to u star t is continuous at t. Without this also you can do, but this is for simplicity. So what is the advantage of this assumption is that now you can write, because it is optimal, I can write equality here. Otherwise I have to put an epsilon and do the epsilon optimally you have to take and so on. So that I wanted to avoid the difficulty here. So it is jx naught t naught u star, now u star dot. Now you can repeat the arguments here, t naught to t naught plus delta, no, I have to correct myself here. So I just cross this. The board is good. Go back to DPP. Okay. My objective is that I want to get the other way inequality, which is less than or equal to 0. Somehow I have to get the other way inequality. For that, go to DPP statement again. it is e power u dot or u hat dot something. Okay. So I want to take here the optimal one. If optimal one does not exist, you have to go to epsilon and u epsilon and so on. I want to avoid that. So assume that such an u star exists. So then I can write this integral t naught to t naught plus delta L of phi s s some u hat something ds plus v phi hat phi s phi t naught plus delta t naught plus delta. So what I am saying is that in the DPP it is infimum is there, assume that it is attained at some u hat star. So you write that equality here. Then you repeat the steps here. All the steps for less than or equal to 0, you do the algebra. Again I am irritating algebraists. You do the algebra, take the limit, and I assume that t going to u hat t is continuous so that you can do whatever we did earlier. Only thing is that instead of less than or equal to, now we will get equality, but when u equal to u star at t naught, is what I am writing. So same procedure. Earlier for every u we got less than or equal to 0, now we will get equality but at u star t naught. Repeat the arguments. So equality holds when u is equal to whatever. So if you start with an optimal infimum attaining u star, you can show that in our inequality it is equal to 0 when u equal to that. So you combine both. So once it is true for every u, I can write every u it is less than or equal to 0. So sup power u is also less than or equal to 0. But that says that at u equal to u star at t naught, the sup is attained and the sup value is 0. Okay, so that is the idea. So conclusion. So we have made some simplifying assumptions. Under the smoothness assumption and some small assumption about the existence of optimality and so on, what we have shown that minus dou v by dou t at the point x naught t naught plus h x t tv x t v is x naught t naught. Okay, I will write because is equal to 0. So where is the junk? H is h x naught t naught p is the supremum. Okay, sup overall small u in capital U minus f x naught t naught u dot p minus L x naught t naught u. Maybe I will rewrite that because it is very important for us. So I will rewrite that. I will rewrite the HAB equation here. So let me erase everything. So we have now derived under some simplifying assumptions, of course, the PDE for value function v. I will rewrite here. Okay, minus I will avoid the variables here. So h x t dv equal to 0 from 0 t. Okay, and we know also that v x t is gx. G is the terminal cost and h is a supremum. hxt of something is minus xtp u dot p minus L xtu sup. So I have to take overall u in u. Okay. Because sup over that is less than or equal to 0, then it is attained also at 0. So we have equality here. So this is the so-called Hamilton-Jacobi Bellman equation. So it's called HJB. Okay, I have a few more minutes. Okay. So under the smoothness assumption, we have derived the equation for the value function. So hoping that we can solve this and get the V. Once you get V, that will come how to make sense of V when V is not smooth. We'll come back to that the next class. But now I want to motivate if V is not smooth, how we will deal with. How what is the weak sense in which we will understand the solution V. If V is not smooth. So it is different from the weak sense Professor Adimurthy talked yesterday. That was based on integration by parts. That we cannot do here because our equation is fully nonlinear. Okay, so we have in this P was my dV. P is my dV. So in the dV, the highest order derivative term, we have nonlinearity. So I cannot use integration by parts like that. So integration by parts we cannot use. So it is, what I am going to say is more towards the maximum principle type of method. Okay. So what you do is that this is a very general method. Okay. In Navier-Stokes also you may in the next week you will come to know about this method maybe more and more, but maybe in a different setting. Okay. So what you do is that anyway before that I want to make a remark to make my life simple, hopefully your life also. What you do is that if you define W is V x t minus t, V is the value function. So this will satisfy the equation because there is only the linear affine transformation in time variable we are doing, nothing else. Okay, x there we are not doing anything. So we have instead of minus here we will have plus. Okay. And now we have condition on time t equal to 0 dgx. Okay, so now it is a sort of forward problem. So I want to make the my arguments here, okay, because this is more standard. Because coming from that equation to this and from that to this is a matter of t to t minus t. So now what we do is that you consider this equation and you add the delta is the Laplace, epsilon is a small positive parameter. This is the typical way lot of people do. And in the Navier-Stokes also you will come to that I think later next week. Okay. So this is the viscous term they call. I don't know more details. Okay. Now what has happened is that from a first order fully nonlinear PDE, if you add that term, it is now quasi-linear second order parabolic PDE. Okay. So it has a classical solution. So I think Professor Adimurthy will talk about that next week, I think. I am not an expert on that, so you can ask if any doubt on that. So basically, for this equation, I can have a existence of a, okay, existence of a classical infinity solution. Okay. For that equation, by the standard theory, by standard means it's no way symbol, so he will talk about that. Okay. So we have W epsilon. So it is a classical solution. We know it exists. Now we can also show that I am sure that you are you know about Arcelor-Scully theorem. I think he has talked about that. Some sufficient conditions for a sequence of functions to be a convergent. So you can verify the conditions of that. They are equicontinuous. In the epsilon variable, these functions are equicontinuous and uniformly bounded, provided you stick to bounded domains. Okay? Bounded domains in Rn, anyway, time is anyway bounded, no problem. So then you have the, through a subsequence, epsilon subsequence, we have a local uniform convergence. Okay, that is what, so Arcelor-Scully theorem you use, but you need a lot of estimates here to do that. Okay, so that Adimurthy will talk about that. So we can show that through a subsequence, okay, this epsilon j xt converges to some epsilon, some w, okay, locally uniformly. That means uniformly on compact subset of Rn cross 0. So because of that, because all W epsilons are classical solutions, what we can say is the limit W is continuous, we can say, because we know that a limit of uniform, limit of continuous functions is continuous, we know. So W is continuous, comes automatically. Okay. So what we want to do? W in some sense is a weak solution. Okay. So you are adding epsilon Laplacian, you get W epsilon, take limit as epsilon goes to 0, we got continuous function W, somehow it is a weak solution. Now what we want is that we want some further properties of W, so that properties we can take it as a characterizing property of W and use it as a definition. So and it should be nice enough for analysis also. So that is objective. Some properties of the limit function W. So yeah, I have time. So some properties of the limit function W. So I want to derive that. So for that you assume that W minus eta has strict local maximum at some point. Okay. Where eta I take as infinity function. So you can take it inside. So suppose there is an infinity function eta such that W minus eta attains strict local maximum at some point. Suppose. So what does it mean? We all know about the maximum minimum, but I just rewrite that. Okay. Meaning of that, around x naught t naught, I have a ball of radius delta. So when xt not equal to x naught t naught, and xt belongs to this ball, whatever ball, delta ball around x naught t naught, then W minus eta strictly less than. So it has a strict local maximum. Now recall that W epsilon j's are smooth functions converges to W uniformly on this ball because this ball is compact. Okay. So W epsilon j minus eta converges uniformly to W minus eta. Uniform convergence. So these two things will give us, instead of this, so now we have for fixed delta that, what you do is that you consider a lot of concentric balls, delta by 2, delta by 3 or so. Okay. You are considering delta, delta by 2, delta by 3 and so on, concentric balls with radius like that. What happens then? Then because of uniform convergence, what you can observe is that sup over the boundary of ball delta k, okay, delta by k, this W epsilon j minus W eta strictly less than W epsilon j minus eta at the point x naught t. This is because uniform convergence for j large. Just because of uniform convergence. Okay. So for each k, I can find j large enough, let me call jk, such that this is strict. Okay. So j large enough, it is true, let it be jk. If you don't want jk, you can still take it as j. Only thing you may have to go to further subsequence. Okay. So sup over boundary of B delta k radius W epsilon jk minus eta is less than, okay, minus eta. So this implies that this function attains its maximum inside the ball. Okay. So it has a local maximum, may not be strict, at some point xk tk inside the delta k ball interior. Okay. Now because xk tk is in a ball around x naught tk, ball radius is delta k goes to 0, so it is clear that xk tk converges to x naught t naught. Okay, so what we have got? So I am going to conclude, just 2 minutes. What we have got? We have this Young expression, this function for k equal to 1, 2, 3 and so on attains local maximum at xk tk. Okay, and both eta is smooth and W epsilon j is smooth. So right, this is a maximum at attains local maximum at xk tk. Both are smooth functions. So what we can say is that at this point, which is dou eta by dou eta at the same point. Similarly, dw, same point. Then we can talk about second derivative also. So d square epsilon j jk at this point, and d square, no, I don't want to talk about d square, just talk about Laplacian because that is my equation. So Laplacian of this smooth function at the point xk tk, and we have Laplacian of the smooth function at the point xk tk. And we have here second derivative is so you think about that because it is a maximum. Okay, so you have that. It's the Laplacian is the trace of the Hessian matrix. Okay, so the matrix of all second derivatives. So we have this, not equality but less than or equal to. Now you substitute in the equation, because we know that W epsilon jk, these are classical solutions. So it satisfies the Petrobri equation the classical way. You substitute, what do you get? Dou W by dou T, it is equal to dou theta plus xk tk dw eta. So instead of wj I can write eta. But here we have epsilon times Laplacian of w, that is less than or equal to that. So I have to write here less than or equal to at the same point. So the w you remove w. Now take limit as k goes to infinity. These xk tk's will converge to x naught t naught eta smooth function. So dou eta by dou t plus at the point x naught t naught plus h x naught t naught d eta, epsilon goes to 0. So this is what we get. So I will conclude. So what we have done so far? Just want to conclude. So we wanted to derive some properties of the limit function w. So that is what we have done. So what we have done? So let me call this as some equation. The star. What we have done? Star holds whenever w minus eta has a strict local maximum at a point x naught t naught and eta is smooth. Okay. So whenever eta is smooth function and w minus eta, the limiting function w minus eta has a strict local maximum, I have the equality star. Now exercise. The strictness here can be removed. Okay. Strict local maximum, strict may be removed. That we have to see. And eta c infinity you can replace by eta c1 for first order equation, second order c2. Okay. These two are exercises. So conclusion now is that the property of the limit function is that whenever w minus eta has a local max, strict I am removing local maximum at a point x naught t naught, eta is c1, then a star has to hold. Okay. Similarly, you can do about a local minimum. Similarly, we can do about local minimum. I am finishing. So what is the statement? So local minimum, what is that? Instead of less than or equal to, you will get greater than or equal to. So whenever w minus eta has a local minimum at x naught t naught, eta smooth, eta c1, that inequality greater than or equal to inequality also hold. You have the two properties of the limit function w. Say it appears that it will give we will take these two properties together as the definition of a weak solution. So we say that w, a continuous function, is a subsolution, viscosity subsolution If for every smooth function at maximum you have less than or equal to, and every smooth function at a local minimum you have greater than or equal to. Subsolution, super solution. If it is both, then it is a solution. So I stop here and continue next class.